Good afternoon. Good afternoon. There we go. Maybe lunch. So I'm Dr. Michael Grieves, and today I'm going to talk to you about digital twins and IoT, and hopefully within 30 minutes you're going to know everything about digital twins that you wanted to know. Or maybe not, but I'm going to give it a try anyway. So what my topic is digital twins and IoT integrating the physical and virtual worlds. And where are the slides moving? And so what I want to do is show you the original digital twin. This was introduced in 2002. It's kind of iffy in terms of it wasn't very well formulated, but it was this idea that we were going to have the physical and virtual and be able to separate the two but connect them. In the lower right-hand corner, you'll see some virtual areas, and it wasn't really well known at that point in time that you could have sub-virtual spaces. In the physical world, you get one space. You screw up there, you screw up entirely, you can't fix it. In the virtual world, you can do it over and over again, and you really don't have a whole lot of issues with respect to being able to do it. So I can take a vehicle and crash test it. In the physical world, I can't sell that vehicle. I can go to the virtual world, I can crash test it over and over again. So that was the conceptual ideal. It didn't even have a name at that time. It was the conceptual ideal for product lifecycle management. The model as it exists today is a lot better, courtesy of my time at NASA where they had some great graphics people. And so there's really sort of three pieces to the digital twin that you need to kind of focus on. On the left side, you have the physical world, the physical space that we've always had since time immemorial, and we still have it, in contrast to some people that think they live in the virtual world, but the physical world is out there. There's sort of two pieces to this model, though, is not only do I have the products themselves, I have the environment that they exist in. On the other side of it is we have this new virtual space with basically these virtual products, but they also exist in a virtual environment. It's not enough to have simply a digital twin. You better have a digital twin in the environment because it's not simply about the geometry of the product itself. It is basically about the behavior of those things and that. And then we connect the two spaces, okay? We basically kept data from the physical world to the virtual world, and then we basically want to use that information in from the virtual world that we develop into the physical space. And why do we do that? Whoa, stop. So the way we do that is the fact that we want to move work from the virtual world, from the physical world that we've done it into the virtual world. And why? Because atoms are getting more expensive all the time, bits are getting cheaper. And so we want to make sure that we can move this information into the virtual world and do the work there. So what I really want to do is I want to basically design the product virtually, test the product virtually, manufacture the product virtually, and support the product virtually, and only when I get it all right do I want to go out and move expensive atoms. And so why do we want to do that? The reason we want to do that is the fact that everybody sort of talks about what is information, but the reality of it is we want to know what information does. And so if I take a task, any task, and most of human life is about goal-seeking activity with minimizing the physical resources. I can divide that task into two pieces. The green part is the most efficient use of resources that take to complete that task, and everything above that is wasted resources. And in fact, the green space in manufacturing is called lean manufacturing. I mean, that's what we really want to do. I can take information, and information is a substitute, not for the resources that I need to do the task, but for everything above that, all the wasted. Now, I'm showing the ideal where basically information replacement for all wasted resources. That's never going to happen in human existence. But to the extent that it can basically replace some, and it's doing a pretty good job at that, some of this information and inefficiencies, we basically have the ability. Now, we can cost the physical stuff, time, energy, material. Information is a little difficult. We don't have a unit of information. I can't buy 6 units of information or 6 wits instead of bits. But what I can do is I have a proxy for that in terms of the cost of developing, manufacturing hardware, software, people's time. Where this works is the fact that the cost of information is going to be less than the cost of wasting resources. And for those of us that have made our living in the computer business, that has pretty much been the case, and it gets better all the time because, as I say, bits get more expensive and information gets cheaper as we do that. And why does information get cheaper? Well, there's a little thing called Moore's Law, and for those of you who are purists, it's really not a law at all. It's basically a prediction by Gordon Moore that basically said we're going to double computing capability and, in point of fact, communications and storage capability, everything associated with that, over time. And so we started off with 2K in the 70s, and today we passed 80 billion transistors on a chip. Just to give you some idea, is that I worked on the first supercomputer, which was the Iliac 4 in the early 70s, and it had 25 megaflops worth of computing capability. Today, you get an Xbox. How many of you have Xboxes? Okay, there's 12 teraflops of computing capability in that. And in fact, the largest supercomputer at the moment is Frontier at Oak Ridge National Labs, and it has 1.1 exaflops. We've gone up 1 trillion times in terms of the amount of computing capability that we've had from the early 70s. So it's no matter that we're doing this kind of capability. So computing capability, so Moore's Law doesn't look very impressive until you do it on a regular graph. And now you can see that the reason we're doing such dramatic changes is that we've reached the inflection point a few years back and we're going straight up. So when I did the digital twin, we didn't have enough computing capability to do what I thought we ought to be able to do. We really are now approaching that, and in point of fact, about 2015, where you can see us heading up, is when digital twins really started to take off, because we really had the computing capability to do that. And so it looks a hell of a lot more impressive if I have this graph rather than a semi-log graph that basically shows a straight line. We're going straight up. And so what we're getting to is the fact in my predictions is we're going to have tremendous amount of computing capability. 2030, my prediction is 7 trillion transistors on a chip, or effectively that. There's other capabilities here, but it's 128 times increase. And in 2040, we're going to have 885 trillion transistors on a chip, or a 16,000 time increase. So we're looking at huge amounts of computing. And my point is, we need to be looking at what our computing capability is going to be and looking at designing for that today as opposed to what we actually just simply have. So we have a tremendous amount of computing, storage, 5G network, 6G network coming online, and we've got to basically be planning for that. So I want to talk to you about digital twin types, because there's different digital twins. The digital twin was always intended to be from the entire product lifecycle. There are some that say, well, I don't have a digital twin until something rolls off the assembly line. And that's not true, because as I said, I want to do as much work as I possibly can in virtual space at the beginning, because it's a lot cheaper and there's a lot less implications of making problems there. So the digital twin types, there are 3 types of digital twins. The digital twin prototype, or the prototypical digital twin, as soon as I have an idea that I'm going to do a product, I'm going to have a digital twin. And so as you can see from the graphics here, is that I have a fuzzy idea what the product is, and it takes shape during this particular process. And by the end of that process, I have the entire product designed. So I have it engineered, I have it tested, I have it manufactured, and I have it supported in order to be able to understand what that product is going to do. These are all the products that can be made. So these are the products and variants that I want to make in my organization to be able to have a product that actually can do it. Again, having a virtual product doesn't do you any good unless you can have a physical product, okay? The physical reality trumps virtual reality all the days of the week. What I want to do is, when I start to make products, I want to create a digital twin instance of that particular product. In my design, I may have had a product that had a tolerance of 0.05 millimeters for a particular unit. When I basically make a product, I don't have a tolerance anymore. I have an exact number. So I want to collect all that. I want to collect, how the product was made, what processes were done with that. I want to make sure that the product was then quality controlled to the right dimensions. And so when I basically have a product, I create a digital twin instance of that specific product. Now, that's an F-35. It needs a digital twin. A paperclip doesn't. So it's going to be dependent on the product itself, and the use cases are going to determine what kind of information do I make on that. And so I basically wanted to make sure that the digital twin instance reflects my use cases of what I'm going to use for it. These are the individual products that are made. So these are all the products that I make. My final digital twin is what I call the digital twin aggregate. And this is where the beauty and power of digital twins come about, is the fact that I can take all my digital twins out there running around in the world and put them together and be able to collect information about them so I can predict their performance. And I'll talk about that in a second. But what I want to do is I want to be able to collect the information and be able to predict it. And that's where IoT comes in, obviously, is I got to be able to capture that information off of these products and be able to in essence, use that information in order to look into the future and understand how my product is going to behave. I mean, I do not want problems to occur with my product that I have to go fix. I'd like to anticipate what those problems are going to be and fix them before they occur. So these are all the products that have been made, and if I collect all that information and do it right, I should be able to be a lot more efficient. I should be able to trade off this information for wasted resources of failures. I mean, what I like to say is I'm a frequent flyer. At 30,000 feet, I do not want a problem. I don't want a problem when the plane is in the, when I'm in the boarding area, because that means a big delay. I like them to fix that problem the next time it goes through the hub before there's even an issue. So in terms of the digital twin model, what we're seeing is an explosion of the scope and scale for tangible products. Now, the digital twins can be intangible, and I've stayed away from that for a reason, because it was tough enough to convince people that I could have a digital twin of a physical thing. But the scope and scale of digital twins in a tangible product area are just exploding all over the place. And so we have sort of traditional products where it started: cars, locomotives, power generation systems, airplanes, ships, oil and gas rigs, and things like that. So very big, expensive items where they're complex products that I need to capture that information. But we're starting to see digital twins of cities. You're going to see a number of presentations here. The digital twins of people and pharmaceuticals. And I want to mention on the people side, it's not digital twins of what people are going to do, because who knows what people are going to do. That's always the interesting thing. But of their physiology. So in terms of digital, we're seeing digital twins of pacemakers and implants, digital twins of people's hearts so that they can do ablation techniques. So we're seeing a whole lot of that kind of capability right now. So this has been exploding since probably the last 7 years. In 2019, I did a Google search on digital twins and got about 1 million hits. I just did it recently and got about 9 million hits. So we're seeing a huge increase in the interest of digital twins. Now, that's the upside. The downside is everybody calls things digital twins, and so you got to be a little bit careful about this whole digital twin nomenclature. But digital twins get a lot of attention. The physical twin is as important, because again, you got to have a product that actually does something. I mean, my idea of quality control is not, did it meet the specifications of the factory? Did it perform for the user the way they expected it to perform? So these physical twins got to do actual work. So we're seeing an explosion of smart products. So they sense the environment, they translate those senses and their electrical impulses into something that we understand. They compare it to what they want to be. So most of life is comparison. Here's where I want to be, here's where I am, and I want to close that gap. And then finally, they need to react, okay? They need to do something. I need to either have humans, informing the humans to do something, or I basically have the autonomous thing do it. Here we've moved into smart connected products. So this is where IoT comes in. Not only do we have to basically have the product be smart, but it has to communicate, it has to assess, and it has to respond to something. And then finally, my last thing, and I think is extremely important, it needs to protect itself. We need paranoid products. The cybersecurity thing about products, especially when we talked about autonomous, scares the hell out of me. So cybersecurity is a huge issue. So let's look at some of the IoT physical sensing. The product's own identity. Who am I? I mean, that's what humans do. Who am I, you know? And so the location of the product or its components, the change in velocity and acceleration, state changes, so all the state changes, both discrete and continuous, from one state to another, such as on to off, not triggered to triggered, like airbags, for example, heat gradients over time. The forces that act, so the environment that I'm in, the forces that act on the product, such as heat, air pressure, gravitational forces. The presence of all kinds of electromagnetic waves, where basically products do a better job than we do because we can only see a certain part of the electromagnetic spectrum. And then finally, the presence of other objects and their mass, shape, and relative speed and direction in relationship to our product. So these are the, and by the way, this is not a comprehensive list. We come up with new stuff all the time, but this is where IoT comes into play, is this idea of basically capturing the physical world into the virtual world and being able to translate that. So as I say, the digital twin gets a lot of response, but the digital twin model is as much about physical stuff as it is about virtual stuff. And I want to really make that point. So IoT is critical to the idea I had about, you know, how do I get data from the physical world and move it into the virtual world in order to be able to get information that I can trade off for wasted resources. So basically, there are two categories of IoT sensing needs, okay? On the left side, we have the physical twin, the product itself, and we basically have to sense the activity of that particular product. And that was sort of a lot of the list that I talked about. But we also have to do IoT sensing of the environment. And so it isn't enough that I basically have the IoT of that plane. You know, it needs to know what the weather is that I'm running into. It needs to know the fact people are trying to shoot the plane down. And the pilot is an interesting aspect of that. So I've got to not only have the IoT of the product itself, I have to have the IoT of the sensing, because it's not enough that the product sits there in space, in its own virtual space. It sits in a behavioral space, and so I have to be able to predict the behavior of that product if I'm really going to do anything useful for that. So where does the digital twin model come into play in terms of IoT and AR? And so you saw my initial model, which was basically this idea of sequential. I do something in the physical world, moves over to the virtual world, and moves back into the physical world. Really, we want to overlay the virtual world onto the physical world. So I want to be able to look at a power supply system and not only see the system itself, but I'd like to see the fan blade, the blade speed. I want to see the temperature gradients. I want to see all kinds of things. So AR and IoT, in my mind, are basically highly connected in terms of wanting to have that kind of information and be able to, at the same instantaneous time. So that means fast cycle times from collecting the information to processing the information to basically then using that in both the physical and the virtual worlds. So in terms of what I can do, these are the three things I think are important: interrogative, predictive, and learning. So interrogative, and this is an example of a rocket engine, but you know, what's the pressure in inland A? So no matter where the product is in the world, I can have the information about it. That's really the axis. We will never have another Malaysian airplane situation where we don't know where that airplane went. We are collecting that information, and that'll never happen again. Predictive, I want to be able to predict what's going to happen, you know, and I want to basically look into the future on that. In terms of then learning, is I have products that are coming out at different time frames. I don't want every product to have to learn by itself. I'd like to be able to take that information from the previous older products and be able to adjust it. In a lot of these cases, we're using software to make those adjustments. So you know, these are sort of the three main areas that I'm really interested in. So I want to take you through the digital twin model through the life cycle and IoT's impact on this. So in the create phase, this is the classic model. I have my physical and my virtual, both products and environments, and I basically want to create this particular product. So it comes into being, and I wind up with the full-blown design at the end. But that's not enough. I got to figure out how to make it, okay? So I basically have to be able to have the means of production at the same time I've got simply the idea. If I've got simply the design, I've got pretty pictures. I don't have a particular product. So in IoT, I need to worry about sensor development. What kind of computing? I'm going to be edge computing, cloud computing. How much capability do I have to have? How am I going to communicate this information? And then the big one is cybersecurity. How am I going to protect this product? Once I start to communicate this thing, I basically, even if I don't have the ability to change it, simply having the information that an adverse person would have will cause me problems. When I go into the build process, this is probably the most complicated because not only do I basically have my digital twins, I got to have the digital twin of my equipment. I take that information and I got to tell the actual machines. So I want to, in essence, pour in raw material on one end and pour out a finished product at the other end. On the far left side, I wind up with a physical product. I want to create my digital twin of that instance. So in the build product, I basically am creating my digital twin instances. And in IoT, I'm worried about IoT integration. So how do I, in essence, build that in? And I think additive manufacturing is really going to be an opportunity to, in essence, print the IoT stuff in. So I'm using my digital twin prototype, and I'm using my digital twin instance. Finally, in the sustain mode, which is the longest period of time, is what the IoT is going to do. So I have my digital twin prototype, my digital twin instance, and then the more information I can collect about the products that are running out there in the world, I'm going to have the information to be able to do predictions. So the IoT, so I need causation. I can live with correlation. In fact, most of the time I'm going to have correlation as opposed to causation. What actions do I need to take? And then I like to, we're humans. Our highest bandwidth is our eyes. We want to visualize that so that we can make good decisions about how that product works. Finally, I want to feed back that information. Too often I see the third instance of the product having the same problems as the first. Why? Nobody told them it doesn't work right. And so we need to get that feedback loop, and IoT is critical for doing that. Kind of last part, I want to take you through where I see the evolution of digital twins occurring. And so if I look at the amount of information, and remember, we have dramatically increased the ability of information that we have against the physical to virtual maturity. At kind of level 0, we had the traditional ones that we've had since time immemorial. As soon as we had an idea about a product, it had to take physical form. We had to sketch it out, we had to create blueprints, we had to create physical prototypes. Okay? In the 2000s, which was interesting, I call it the transitional, a lot of the technologies that we're talking about basically started to come about. Obviously, digital twins were one of them, but IoT, okay? When I proposed the first model, there was no such thing as IoT. There was a thing as what we were doing, but we didn't have a name for it. 3D, when we moved from 2D to 3D, that was a quantum leap in how we looked at things. So that was a transitional period to have these technologies. AI starts to come along, machine learning starts to come along. Today, we're in the conceptual era. So we have digital twins, but we have to do a lot of the work to pull that information together. We have a lot of work to do in terms of interoperability of different digital twins, and I don't have time to talk about that, but that's sort of my big issue right now, is how do we have the different digital twins we have be operational. So I call it this ad hoc thing. We're making our own digital twins. The next stage I see is replication, is this idea that we will have platforms for digital twins that will allow us to be able to have this information in fully formed digital twins, and they will all operate together. So we will be able to, say, take an airplane, its fuel system, and its engine, and not only have different digital twins of those, but when I add fuel to the fuel tank, it's going to increase the weight of the entire airplane. But finally, I'm going to basically have this idea of front-running simulation. And this is where I think it's going to get really, really interesting, because if you'll notice sort of my diagram, I have this crystal ball up there. Front-running simulation is this idea that we basically have a projection of the future, okay? So most of life is avoiding adverse events, and we're not really great at doing that. But if I could, at every time 0, run a new simulation of what's going to happen. So I have my assumptions, and too often what we do now is we get these great simulations, We start to develop the product. As soon as that's done, we put the simulation in the drawer, never to be seen again. I want to run that simulation at every time zero and predict out in the future. Now, we won't be perfect. Anybody gone to have somebody do a reading from a crystal ball? They're not perfect either. But what we want to be able to do is to basically be able to then give us probabilities. For example, there is a 70% probability in 2 weeks it's going to fail. It's going to be a 90% probability in a month. So again, as I said, I don't want to have a problem with the product itself. In fact, my difference between Industry 4.0, and I'm not quite sure what Industry 5.0 is at the moment, but Industry 4.0 is about taking the time from an adverse effect to the remediation and dropping that down. I never want to have that problem. I want to basically be able to predict that those problems are going to occur and be able to replace them before they happen. So we're going to move from periodic maintenance to predictive maintenance. What it's going to mean is, will I replace some things a little too early? Maybe, probably, definitely, we will. But I am going to basically make sure that I don't have failures. Failure on the factory floor is extremely costly. And failure everything else is also costly. So this idea of front-running simulation is going to be really kind of key. I just want to finish up with the fact that there's some digital twin selected resources out there. There's this idea of intelligent digital twin versus the current digital twin that we have. It's a paper that's out there on the website. You can go to my ResearchGate page, or you can find it in pretty much a lot of these areas. And I also have a YouTube channel out there that basically explains a number of my presentations, maybe in a little more detail than the 30 minutes I was allotted today. And with that, I'd like to thank you for your attention. I know it was quick, and I covered a lot of things. I will put this presentation out on my YouTube channel, and also the actual slides that you can have access to. And with that, I thank you very much for your attention, and I think we're done. Thank you.